Hi, I'm Mark Barsimian. In this video, I'll be discussing matrix representations of graphs. This material is from Chapter 10, Section 10.2, Matrix Representations of Graphs. Pages 698 to 703 are relevant to this video, examples 1 to 5 of that section. The homework is this short selection of 3 exercises from Section 10.2. I'll be reviewing matrix terminology. I'll introduce what's called the adjacency matrix corresponding to a directed graph, and then I'll discuss the adjacency matrix corresponding to an undirected graph, and then finally I'll be discussing matrix block forms corresponding to connected components of graphs. So we start with a review of matrix notation and terminology. These words in print, an M cross N matrix A over a set S, are spoken this way: an M by N matrix A over a set S. This symbol denotes those spoken or written words. What it means is a rectangular array of elements of S. When you say over a set S, that's telling you what set these elements in this rectangular array are drawn from. And the key thing to remember is the number that gets mentioned first, the M, is the number of rows. M rows. The number that gets mentioned second is the number of columns. Notice that the symbols for the entries of this matrix have 2 indices in the subscript. There's an I and a J. The I is the row index. So that I goes from 1 to M, 1, 2, 3, and so on, all the way down to M. Whereas the second index, the J, is the column index. Notice that the J goes from 1, 2, 3, and so on, all the way up to N. There's additional matrix terminology and notation. When we say the ith row of A, it means this: the elements of that row in the matrix described as a matrix of their own. So notice that that is a 1 by n matrix. It's got just one row, it's the ith row, but it has a column for every column of the original matrix A. Matrix A has n columns, so this row matrix has n columns. What's called the jth column of A is this. That's that column of entries displayed as a matrix of their own. So notice that it's a single column, but it has a bunch of rows. It has a row for every row in the original matrix, so it has m rows. So the jth column of A is an m by 1 matrix. This entry denoted A subscript ij is called the ijth entry, and an m by n matrix is said to have size m by n. To say that 2 matrices are equal means that they have the same size and all their corresponding entries are equal. That is, A subscript ij equals B subscript ij for all combinations of I and j. A matrix for which the numbers of rows and columns are equal is called a square matrix. And in a square matrix, the main diagonal is the entries that have subscripts like that. The ij subscripts are the same. To say that a matrix is symmetric means the ijth entry is the same as the jith entry. Now I want to talk about the matrix corresponding to a directed graph. It's going to be called the adjacency matrix. If you use those words when G is a directed graph with ordered vertices V1 to Vn, then it means the n by n matrix over the set of non-negative integers, so integers that can be 0 and 1, 2, 3, and so forth, but they can't be negative, defined by this: the ijth entry of the matrix is equal to the number of arrows from vertex Vi to vertex vj. So for example, find the adjacency matrix for this directed graph. Well, we have to start by knowing how big a matrix to make. We have 4 vertices, so that means we're going to have a 4 by 4 matrix. So there's a 4 by 4 matrix. We have to figure out what goes in this spot. That's the number of arrows from vertex 1 to vertex 1. Well, there are no arrows from vertex 1 to vertex 1. So there's a 0 there. What about the entry that goes there? That's going to be the number of arrows from vertex 1 to vertex 2. Well, there are no arrows from vertex 1 to vertex 2. So a 0 goes there as well. Now this is pretty tedious. It might be simpler to just figure out what all the arrows of the graph correspond to and put those entries in the matrix. So let's start with this. Edge 1 goes from V2 to V1. So there's 1 arrow from V2 to V1. So there's a 1 that goes here. Edge 2, oh, I've got a typo here. This should say E2. Edge 2 goes from V2 to V3. So there's 1 arrow from V2 to V3. So that means that a 1 goes there in the matrix. Edge 3 goes from V3 to V4. So there is 1 in that cell. That arrow goes from vertex 3 to vertex 4. Edge 4 goes from vertex 1 to vertex 4. So that corresponds to a 1 in the matrix at that position. And finally, arrow 5, edge 5, goes from vertex 4 to vertex 2. So that corresponds to a 1 in the matrix at that position. So all the other entries of this matrix are 0. So there's our 4 by 4 adjacency matrix for that directed graph. Example 2. Draw the directed graph for this adjacency matrix. Well, notice that this matrix is a 6 by 6 matrix, so we need 6 vertices. I'm not going to think too much about how to arrange the vertices. I'm just going to put them in a circle. So there are 6 vertices. Let's get to work. This 2 indicates that there should be 2 arrows from vertex 1 to vertex 3. This 1 indicates that there should be 1 arrow from vertex 1 to vertex 4. This 1 indicates there should be 1 arrow from vertex 1 to vertex 6. I can continue in this manner, and it's all fairly straightforward. I'll do this collection of entries. Those tell us about the arrows that start at vertex 2. There's 1 that goes from vertex 2 to vertex 1. There's an arrow that goes from vertex 2 to vertex 2. That's got to be a loop. And there's got to be an arrow from vertex 2 to vertex 5. What does this row of the matrix tell us? There's got to be an arrow from vertex 3 to vertex 2, 2 of them, and there's got to be an arrow from vertex 3 to vertex 1. This row of the table tells us that from vertex 4, there is a single arrow that goes to vertex 1 and a single arrow that goes to vertex 6. This row of the table tells us that from vertex 5, there's a single arrow that goes to vertex 4 and 2 arrows that go back to vertex 5. So 2 loops at vertex 5. And finally, this row of the table tells us there's a single arrow coming from vertex 6 to vertex 3. That's it. Let's go on. Now I want to talk about the matrix corresponding to an undirected graph. The same words, the adjacency matrix for graph G, if those words are used in the case of an undirected graph with vertices 1 to n, then it means this. It's an n by n matrix over the set of non-negative integers defined by this prescription. The entry aij is equal to the number of edges connecting vi and vj for all combinations of I and j. So for example, find the adjacency matrix for this undirected graph. Well, this is a graph with 4 vertices, so we need a 4 by 4 matrix. Well, let's just start by noting the edges. Edge 1 connects vertex 1 and vertex 2. So that means that there should be a 1 in cell 1, 2, but also a cell in 2, 1, because there is an edge connecting vertex 2 to vertex 1. Now let's think about edge 2. Here I have a typo. I'm missing edge 2. Edge 2 connects V2 and V3. So there should be a 1 here and also a 1 here. There's an edge that connects V2 to V3, and that's the same edge that connects V3 to V2. What about vertex 3? It connects V3 to V4. So that means there's got to be a 1 here and a 1 here. What about edge 4? Edge 4 connects V4 to V1, so that means there's got to be a 1 here and a 1 here. And finally, edge 5 connects V2 to V4. So there's got to be a 1 here and a 1 here. All the other entries in the table are 0. There's the adjacency matrix for that undirected graph. A couple of observations. Notice that undirected graphs will always have adjacency matrix that are symmetric. Now, when drawing a graph that corresponds to a given adjacency matrix, if the matrix is not symmetric, then you know the graph has to be a directed graph. Now, why do we know that? Well, that's basically the contrapositive. If the graph is undirected, its matrix will be symmetric. So if the matrix is not symmetric, then the graph must not be an undirected graph, so it's going to have to be a directed graph. On the other hand, if the matrix is symmetric, then there is a corresponding directed graph, and there's also a corresponding undirected graph. So for example, for this given adjacency matrix, draw the corresponding directed graph and draw the corresponding undirected graph. Well, either way, we need 5 vertices. This row tells us that there's an arrow from vertex 1 to vertex 2 and 2 arrows from vertex 1 to vertex 4. This row tells us there's 1 arrow from vertex 2 to vertex 1, 1 arrow from vertex 2 to itself, that's a loop, and 1 arrow from vertex 2 to vertex 5. This row tells us that there are no arrows coming out of vertex 3. This row tells us that coming out of vertex 4, there are 2 arrows going to vertex 1 and 1 arrow going to vertex 5. This row tells us that coming from vertex 5, there's 1 arrow going to vertex 2 and 1 arrow going to vertex 4 and 2 arrows going to vertex 5. So in other words, 2 loops. So there's a directed graph corresponding to that adjacency matrix. What would the undirected graph look like? Well, basically, every one of these double arrow pairs just gets replaced with a single edge. So these 2 matrix entries correspond to that 1 circled edge. This matrix entry corresponds to this loop. These matrix entries correspond to the 2 edges that connect vertex 1 to vertex 4. These matrix entries correspond to the 1 edge that connects vertex 5 to vertex 2. These matrix entries correspond to the 1 edge that connects vertex 5 to vertex 4. And finally, this matrix entry corresponds to the loop, the 2 loops at vertex 5. So there's the undirected graph that corresponds to that same adjacency matrix. So again, if an adjacency matrix is not symmetric, then the graph can only be a directed graph. But if the adjacency matrix is symmetric, then there's both a corresponding directed graph and a corresponding undirected graph. Now I want to talk about the matrix block forms corresponding to connected components of graphs. I'll introduce this by doing an example. Find the adjacency matrix for this graph. Well, that's a graph with 6 vertices, so we need a 6 by 6 matrix. All right, we have an edge connecting V1 and V2. So that means there should be a 1 in this cell and also in this cell. We have 2 edges connecting V1 and V3. So there should be a 2 in this cell and this cell. There's 1 edge connecting V2 and V3. So that means that there should be a 1 in this cell, in this cell. There's an edge connecting V4 to itself and an edge connecting V4 to V5. The edge connecting V4 to itself shows up here. The edge connecting V4 to V5 shows up here and here. And then finally, there's an edge connecting V6 to itself. There's a loop. So that shows up as a 1 here. The rest of this matrix gets filled up with zeros. Notice something about this matrix. There are really 3 blocks in this matrix. There's that collection of cells, and there's that collection of cells, and then finally, there's that cell by itself. All of the other cells are 0, and they can be kind of grouped in the following way. So there are those 3 colored blocks along the diagonal, and then those 6 blocks full of zeros that are off the diagonal. Well, that is the gist of this theorem about the matrix block forms corresponding to graph connected components. If a graph G has connected components G1 to GK, and each of the connected components contains n vertices, n subscript I vertices in component G subscript I, and if all the vertices are numbered consecutively in this manner, so the first batch of numbered vertices are in the first connected component, and then the next batch of sequentially numbered vertices are in the next component, and so forth, then the adjacency matrix has this what's called block form. There are blocks of entries along the diagonal, and then off diagonal are matrices full of zeros. So notice, there we've got our 3 connected components. There's connected component number 1, there's connected component number 2, and there's connected component number 3. Those 3 connected components correspond to those 3 blocks on the diagonal. This connected component corresponds to the red block. This connected component corresponds to the green block. And this connected component corresponds to the blue block. Notice that those matrices on the diagonal are square, but the matrices off the diagonal are not square. So in this symbol, each of these colored dots on the diagonal, each of these symbols, A subscript K, or A subscript I, and so forth, those represent a square adjacency matrix for that particular connected component. And then the symbols that are off the diagonal represent matrices whose entries are all zeros. So a couple of remarks. Again, each of the matrices on the diagonal is a square matrix, but the matrices represented by the symbols 0 are usually not square, and they're usually not the same shape. So notice, this matrix is 3 by 2. This matrix is 3 by 1. They're not square, and they're not the same shape. The only time that the matrices represented by the 0 symbols are square is when all of the diagonal matrices A subscript I are the same size. That is, when they all have shape n by n for the same n. So in that case, then, not only will all the matrices represented by the 0 symbols be square, they'll also be the same size, n by n. Now, a remark on that theorem. It's crucial that the vertices be numbered in a way that the sequential groups of vertex numbers correspond to connected components of the graph. If this numbering scheme is not followed, then the corresponding adjacency matrix will not have the block form as described in the theorem. So, for example, find the adjacency matrix for the graph from that previous example, but with this different vertex numbering. Well, let's just get to work. All right, we have an edge connecting V1 to V6. That means there will be a 1 in this cell and also in this cell. We have two edges connecting V1 to V5. So that means that there should be a 2 in this cell and also in this cell. There's one edge connecting V5 to V6. So that means that there should be a 1 here and a 1 here. There's an edge connecting V2 to itself and an edge connecting V2 to V4. So there should be a 1 here and a 1 here, and also a 1 here. And then finally, there's an edge connecting V3 to itself. That means there should be a 1 here. All the other entries are 0. So this matrix does not have that block form. So it's the same graph, but just different labeling of the vertices. So there's a remark in order then. If an adjacency matrix does not have the block form described in the theorem, that does not necessarily indicate that the corresponding graph is a connected graph. So for example, let's go back and look at the matrix given in example 4. This matrix does not have that nice block form where there are square matrices on the diagonal where all the non-zero terms are located, and then off the diagonal outside of those blocks everything is 0. Does not have that block form. But the graph does have two connected components. So the adjacency matrix does not have the special form, even though the graph has two connected components. So the matrix does not have the block form described in the theorem, but the corresponding undirected graph has two connected components. Of course, if we had labeled the vertices of the graph as described in the theorem, then the adjacency matrix would have the block form. Another remark on that theorem. If any of the matrices in that block form is asymmetric, any of the matrices in this block form, any of those matrices along the diagonal, if any of those matrices is asymmetric, then that matrix A can only correspond to a directed graph. On the other hand, if all of the matrices A subscript I along that diagonal in that block form, if all of those are symmetric, then there's both a directed graph corresponding to matrix A and an undirected graph corresponding to matrix A. For example, draw an undirected graph for this adjacency matrix. Well, we're going to need 6 vertices because it's a 6 by 6 matrix. Okay, let's get to work. Those two entries that have a 2 in them tell us that there are 2 edges connecting vertex 2 and vertex 1. This entry that's a 1 tells us that there's a loop at vertex 2. This entry tells us that there's a loop at vertex 3. These entries tell us that there's a single edge connecting vertex 4 to vertex 5. And that's it. So notice that we have 4 connected components. Let's identify 4 blocks in our adjacency matrix. So that adjacency matrix has 4 blocks. The yellow block actually has no numbers in it, but that indicates that this vertex 6 is an isolated vertex. Well, that's the end of that example, and that's the end of the video. Thank you.